In this lecture, I want to talk about recursion in Lattice. Right, so far we have avoided recursion, but we can definitely write programs in our Lattice syntax that are recursive, right? They might not be able to run properly. So like, let's write the factorial function. So let fact be, right, it's going to be a function, takes in an x. And what does it do? Well, if x is less than or equal to 1, we're going to return 1. Else, let me put the then statement. Then 1, right? Else we're going to call x times factorial of x minus 1. Right, you should be able to do this easily in any language, be able to write up a factorial function, and then we might say in fact of 10, or fact 4. Right, this is our basic thing, and what's the problem here in terms of Lattice, right? Why won't this be allowable in our language? Well, let's think about what's actually going on when we do our evaluation, right? So in this let statement, we're going to bind this element, right, this identifying string, to a closure of this whole thing, right? What does that closure look like? Well, it's going to be closure with right, the parameter name x, and then the body of the statement, which is this whole thing, right? So it's this if then else, and we saw how we implemented if then else before, and so we're going to have this expression, which is less equal ident x const 1. That's the first term, right? And then we have the body of the expression. Then we have the then, which is just going to be const 1. And then we have the else, which is going to be, right, a mult of x, ident x. And then this function call, fun call on ident fact, comma, x minus 1, ident x. Right, we should have technically a full minus ident x const 1. Right, so if I have enough closing brackets on there, then this closure is exactly what's going on here. Oh, and we also need our local environment, which at the moment, right, there's nothing else going on, is the empty environment. And what's the problem here is what happens when we do our call on fact of 4, right? That was what we described as fun call, right? And we have two statements. We have the first expression, which is going to be ident of fact. And then our second expression is going to be const of 4. And what did we say the evaluator did when we saw this? Oh yeah, and we're going to bind this to fact in our environment, right? This is an extends. Our whole environment's going to look like this, right, at the moment. So we're going to extend an empty environment with fact, whose value is this closure, right, which is basically the parameter value, the body, and then the empty environment. It's on the inside. There's another empty environment here. That's at the end of the extend statement. Right, so what we're going to do is we're going to look up ident in this environment, and we're going to see this closure. Right, and then what are we going to do? We're going to evaluate this little chunk. We get 4, and then we're going to bind it to x, and then we're going to call this whole unit right here, and let's call that bn, right, for the body, b expression, as it's the expression of the body of this function. And we're going to end up calling, right, evaluating b expression with the following extends the following environment, right? It's going to be x bound to 4, and then the local environment of our closure, right, which is an empty environment. Well, what does B expression look like? It looks like this, right, the if then else statement. And what's the one thing that is not in this environment? Well, I see X is in the environment, so I can definitely do this part and this part and this part, but fact is not in the environment. And that's kind of a problem. That's the fundamental issue with recursion going on here, especially in this form of closures, where the idea is in our environment we have an entire copy of the local environment. Now imagine what would happen if we were able to actually get the definition of fact into its own environment. Well, what is the value of fact, right? It is this closure. So it'd have to have an entire copy of this closure inside of its own environment, which would also need an entire copy of this enclosure inside of its empty environment. And we get this big chicken and the egg situation. I really like, if you've ever seen, sometimes there are textbooks that have a group of happy students standing around, and one of the students is carrying the textbook with the exact same picture of the students happily standing around, and they have a little textbook in there. It's the same issue, right? The closure, the camera shot that we took at this moment, right, that's the closure of the environment of the function definition. And we see all the component parts there, but we have this little recursive form which also needs to have the full picture. And that also has to have the little full picture in there as well. So defining functions using closures like this prevents us from being able to do recursion sort of simply. In the C and C++ world, we don't really have this issue. In the compiled languages, we don't really have this issue because instead of closures, right, we typically just have a pointer to the body of the function. And so this just ends up resolving to a pointer that points back up to the top. And so we just, because everything is in these references and pointers, we don't really have that issue. But the fact that we're trying to do this static scoping structure where the environment contains everything the function might need in order to be able to run properly, which means it needs to contain the entirety of its own definition ad nauseum, that's a big issue. So we're going to learn how to break this recursion, right? So how do we get the chicken out of the egg and get something in between first? Or more so, how do we build up this picture for the yearbook or for my textbook? So let's think about how we build up this. Let's think about the picture image for a second. Let me clear this off first. Yeah, so if we think about how they actually did this, right? They took this picture of these students, and the student was holding like a green book, right? That was just blank. And then once they developed this photo, right, the local environment, there was just a placeholder there basically. And once they developed the photo, they then went in and replaced this little unit with a full copy of the original photo, right? And then you could do that again a couple of times until you can't notice the difference anymore. So we actually do this by adjusting the photo after the fact, right? Not at the closure time, not at the camera shot moment, but later on we go through and we fix the recursion issue. So how are we going to do that with our language? So remember we had, right, everything's an expression. We have all of our arithmetic. We have all of our conditionals. We have an if then else. We have our let statements. We have our fun def. And we have a fun call. And then we're going to add let rec. And what is this going to do? It's going to take in a string, which is going to be the name. Right, we can't really do anonymous recursive function calls because, right, we need to call the function from inside of itself, so we need to know what its name is. So we can't just have it fully anonymous, right? We have to have a name. So we're going to get around it by having a new let statement, right? Let rec takes in a name, it takes in the parameter, which is going to be an expression, and it's going to take in a body, right? The body of the function. And the idea here is that I want to be able to say something like, I want to basically take this definition, but now we're going to just say let rec. And that's how we want to handle the concrete syntax, right? So again, what is necessary here? Yeah, I see we have our name, that's here. We have our parameter string, that's this expression. And then we have a body here, which is going to be this unit, right? The body of my function. So that's not too bad. It's basically the exact same structure as our normal lets, and combined with our structure for fundef. In fact, this should be a string. Sorry, there should be two strings. Right, because fundef is a string and a body. So this should be expression. There we go. So yeah, how are we going to break the circularity? Well, we're going to do it by extending our environment. So let's come back to this let rec statement. So far, I hope it's fairly clear that all it is a combination of fundef and our let statement combined together. And the way that we're really going to handle this is by how we do lookups in our environment. So remember that our environment, this was also an abstract syntax structure, right? Where we had an empty environment. We had this extends environment, which, right, we could take a string and a value and another environment, right? And this was a way that we basically made a little cons list to keep track of the nesting values of our environment. It's an easy way to handle shadowing, because as we extend them out, the earlier or the later elements, the later definitions just naturally shadow the earlier definitions, because as we go through our lookup function, we eat up the extends, right, one at a time, and then we recurse into the environment as we go. And we're going to extend this by, or we're going to add one more type, which is called an extend rec. And what does this do? Well, instead of just, right, how did we handle functions before? We just had whatever name we were going to give it, right? Let fac, that'd be the string here. And then the value was a closure, right? Closures are a first class type of value. And so the way that we handled normal functions is we just added it to our environment, right? Our old environment, a closure, and the name that we were going to bind to it. Now, what we want to do is we actually want to compose the closure on the fly. So I want to keep track of all the information I actually need in order to make that closure, but I'm not actually going to store the closure, right? This is kind of saying, like, I'm going to make sure that this student is carrying something that's book-like so that I have a place for it to go, but I'm not actually going to make sure that the book is correct right now, right? I'm just going to keep all the component parts that I need so that later on when I actually print this picture out, I can then do some photoshopping and do the editing that I need later. So we're going to do extend rec, and what do we need? Well, we need a string, right? That's going to be the name of the function. We need a value, or we're going to keep track of, instead of, right, what's in a closure? We have a string, which is the parameter. We have the body of the function. And then we had the environment that was in existence when we defined this closure. So we're going to do the same thing. We're going to keep around the parameter name. We're going to keep, we're going to keep the name that it's bound to. We're going to have the parameter name, which is another string. We're going to have the body, which is going to be an expression. And then we're going to have the local environment when we defined it. Because we still want static scoping, so we want to keep track of all of the variables that we have defined up until we define our recursive function. So we want to keep track of that environment, but we're going to do something a little tricky when we do the lookup. So the idea here is we're extending our environment like this, and now we have to figure out what does it mean when we do a lookup, right? So our lookup rule we already saw what happened with the empty environment. We decided that we'll throw an error, right? That means that we didn't find the value that we're looking for because, right, we look up a string. In some environment, right? And what do? We know that if environment looks like extend with this string, let's call it S, with V, and then some other old environment, right? Then we just return V. This is a normal lookup, right? If we look up S in an environment, and environment has the form of extend S, or let's call it T, V old environment, right? Where S is not equal to T. Then we just do a lookup on old environment. Right, so the idea is that if we don't match at the current head of this list of maps, we just recurse down to the old environment. And so those are the two, we could do lookup found, and then lookup recurse, or continue. Right, and then we had one more which said that lookup of S, and if env is the empty environment, well, then we didn't find it, right? So we return an error, right? So this would be a lookup empty. So that handles all of the cases for empty environment and extends. And now we want to talk about extend rec. So what happens when we do lookup of some string in an environment? And I'm not going to handle the error case, right? The case when we get an extend rec that's not equal to the S that we're looking for. So that's obviously going to be an error. But we could have, right, env could look like extend rec of, let's see, we need a string that's it's going to be its name, so we're going to hope that it matches S, right? And if that's the case that we're going to look at. Then we need a string. It's going to be the parameter. Let's call that X. And then we need an expression. We'll call that the body. And then we need the local environment. So I'm going to call that F env, or the old environment. No, yeah, that's fine. I don't want to get it confused with this environment down here. Cool. So yeah, if our environment looks like an extend rec, right, and the S matches, right, so this is the correct function that we're looking for. Well, now we have all of the component parts that we need. We have X, we have the body of the function, and we have the old environment that we had set up. And so what do I want to do? Well, I want to, right, return a new closure, right? That's the whole point of this, was we want to return a new closure that is associated to this function, but now has a recursive definition of itself in there, right? Because remember, fn doesn't have the function called s in there yet, right? This is the definition of that, and this is sort of the whole point, was that fn didn't contain s as this current function. So we want to define, we want to return, right, a closure. And what does the closure need in it, right? So the closure, it takes in, it will be x, right? It needs a string, which is the parameter name. It needs a body. And this is the trickiest part, right, is what environment do we pass back? If this was a normal function, we'd pass back fn, right? That's the local environment at the moment of definition, and that's the environment that we need. But we need an environment that contains its own definition, right? So we're actually going to pass back this entire thing, right? Which is what we called env. So we're just going to say env here, right? And that almost looks too tricky. That almost looks too simple. But really what it is we are remaking this whole extend rec sx body fn. So I'm going to rewrite this in fuller notation. So we have closure x body, and then the environment that we're passing back is extend rec sx body fn. And that's how we get a recursive definition. That's how we break this circularity that goes on, is instead of actually storing the full recursive environment, right? The problem that we had was that the environment that we store here does not, that we evaluate the body under, does not include the definition of fact yet, right? So what we do is we just extend our definition of environment to keep all the component parts that we need to build this closure on the fly, right? So whenever you look up a recursive definition, I'm going to give you a closure that contains the recursive definition, right? I didn't actually have to keep this all fully expanded as a closure that contains a closure that contains a closure that contains a closure. I am just going to pass you back all of the parts that you need in order to build that out. Just like over here, we didn't actually need them to make another copy of the book for us, right? We just held up the placement that it would be, right? All the parts that we need in order to develop this. And then the moment that you actually print the photo out, you go back and you make a copy of that photo, and you paste it into your current copy, right? So the current copy of my factorial function, right, when I look it up, it generates a new closure that has the factorial function, as well as the definition, plus the environment that contains the definition of all the parts of the factorial function that we need. I think this is probably one of the trickier things that we cover in this course, mostly because we're thinking about, recurrent stuff, and how do you break that loop, right? How do you actually get out of that sequence? And the way we do it is by extending our environment, by adding a new thing that is just the component parts, right? So now we sort of think, well, we don't necessarily have a closure in my environment, but I have this wild, crazy extend rec that contains stuff like that. I hope this is clear enough. We will go a bit more into another way to do recursion, but this is a nice way that we can handle it, and there's examples in the notebooks as well that you can go over.